Hey folks, I welcome you all to Scalar Academy's YouTube channel. So, if you want to be a good programmer, then you need to have a good mathematical aptitude. Or, in other words, you need to have mathematical way of thinking to solve the coding problems which you face. So, understanding the importance of this, we have brought you this tutorial on mathematics for programming. Now, before we start off, I'd like to request you guys to subscribe to our channel and also hit the bell icon so that you do not miss out on our upcoming videos. So, on that note, let's get started.
Hello, so we are back with a live class. Today's topic is factorization. These classes are for people who want to become better programmers, right? Better at DSN algorithms. So please make sure that you subscribe to the channel and press the bell icon to get notifications, right, about any new videos. As always, there will also be a practice set available to you. This practice set will have a few problems so that you can apply whatever you learn in today's class, right? Actually practicing the problems will help solidify the concepts. All right. So we are going to cover factorization today. Now, factorization is a topic of mathematics. All right. And as computer programmers, you will need to have a decent understanding of mathematics. In fact, in all sciences, and computer science is a science, right? The stronger you are at maths, the easier your life will be. Now, programmers, you don't have to be very good at mathematics, but there are certain areas that you need to focus on to be a good programmer. Now, these topics are like discrete math, probability, statistics, combinatorics, linear algebra, modular arithmetic, number theory, graph theory, right? So it is still a very large section of topics that you will need to be a very good programmer. So we're going to start with that. And today's topic is from number theory, and the topic is factorization. All right. So let us begin. All right. Cool. So before we begin, let us start with a question directly, right? Let us say that you have been given a number n, all right? And this is an integer. This is an integer. In fact, this is a positive integer, right? Your task is to find all the factors of this number, right? So for example, let us suppose that you have a number like 16, perhaps, right? So can someone tell me all the factors of 60? What all numbers is 60 divisible by? So when we're talking about factors, we are talking about the positive numbers, right? The positive integers that divide 60, right? And do not leave a remainder. So what numbers are those? So firstly, we have 1, right? Then does 2 divide 60? Yes, it does. So we have 2. Similarly, 3 divides 60. 4 also divides 60. 5 does. 6 does. 7 does not really divide 60, right? Now 8 also does not divide 60. Neither does 9. 10 does. Right? 10 definitely divides 60. After that, what numbers we have? So we have 12, right? Then we have 15. Then we have 20, right? What more? We have 30 and 60, right? So these are all the different factors of 60, right? Cool. Now, before we dive further into this problem, let us try to draw some observations. Right? Let us try to draw some observations and see if there is some pattern to what the factors of a particular number are, right? So first of all, you will notice that 1 and the number itself, they are always factors of this number. Yes, do you agree? Well, 1 divides every single number, and if you have a number, let us say n, then that number will divide itself, right? So that has to be a factor. What else do we notice over here? Is there any other pattern that we notice over here? Yes? So we notice one more thing. So the first thing is that 1 and n are divisors of n. The second thing that we notice is that factors come in pairs. Factors come in pairs. What do I mean by that? I mean that given any factor, there is a corresponding factor, right? So if I pair 1 with 60, then I will get 60, right? 1 times 60 equals to 60. Similarly, if I pair 2 with 30, then I once again get 60. So 2 times 30 is 60. Similarly, 3 times 20 is 60. 4 times 15 is 60. 5 times 12 is 60. 6 times 10 is 60, right? And then if I continue from here on, you will see that I will just repeat these things, right? So I will just repeat these things. I will say 10 times 6 is 60, right? So 10 and 6 have been repeated. Similarly, I will next say 12 times 5 is 60. So after all this, the numbers are being repeated. Is that clear? The factors will always come in pairs, right? That is the main observation that we draw from here. All right. Now, given that we have these observations, could we write a program? Could we write a function, let us say find factors, right? That takes an integer n, and let's suppose prints out all the factors of it. So let us in fact call this, instead of find n, let us call this print factors. This function accepts an n, and it is supposed to print out all the different factors of n. Right. So what approach do we see over here? So one way to do this would be the naive way, right? The very simple way. The first way would be to go through all the numbers, go through all the possible devices, right? So to go through all the possible devices, we will need a few more observations, right? Let us quickly see what those observations are. So the first observation was that 1 and n are devices of n. There is one hidden observation over here, right? Let me mark this as the third observation. And that observation is there are no devices that are less than 1, and there are no devices that are greater than n, right? So the devices, so 1 is the smallest divisor and n is the largest divisor. Yes? Does that make sense? So when I am trying to find the devices of a particular number, I only have to go from 1 all the way till n, right? Because I cannot have devices that are greater than n. Does that make sense? Is that part clear? Right? Perfect. So how do we write this program then? This is a very simple for loop. So we will say for I goes from 1, right? All the way till n. And we'll increment I. So we'll go through all the different numbers. What we will do inside this? We will check if n mod I equals to 0. Right? So everyone is familiar with this mod operation, right? This is the remainder operation. This says that when we divide n by I, then what is the remainder? Is that remainder 0? If that remainder is 0, then I must be a factor, right? I must be a factor. Then what do? We simply print I, right? So this is our code for factorization, right? Cool. Now this is the first approach. This is very naive. We can do much better than this. But why is this naive? So let us analyze the time complexity of this particular program. So how much time does this take? If I have a number n, then what is the time complexity of this particular program? Well, this is a simple for loop, right? We are going from 1 all the way till n. So this is linear. In fact, this takes order of n time, right? Cool. Can we do better? Well, certainly we can. So the first thing that you will notice over here is that whenever you are looking at these numbers, we know that the largest factor is the number itself, right? The largest factor is the number itself. But what is the second largest factor? How big can the second largest factor be? So I know that the largest factor is n itself, right? What about the second largest factor? That must be less than or equal to n by 2, right? That factor must be less than or equal to n by 2. Why? Because if it is greater than n by 2, then its corresponding pair, right? Devices always come in pair, right? Factors always come in pair. Its corresponding pair will not be an integer. Right? 2 is the smallest integer that might divide this number apart from 1. Right? So we know that the second largest has to be less than or equal to n by 2. So one thing that we can do over here right away is, instead of having this loop from 1 till n, right? Instead of having this loop from 1 till n, we can modify this. Right? We can modify this. So let me just modify this over here. I will say I is less than or equal to n by 2. Right? And notice that this is integer division over here. Integer division. Right? So in this loop, I will print all these divisors, but now I do not print n, right? I have missed n now. So I will have to add another statement over here, which will simply say print n. Is that clear? Because now our loop is going from 1 all the way to n by 2. So I will not print out n in this loop. I'll have to print it separately. Yes? So how much time did we save just now? We made a program twice as fast. Right? That's very nice, right? We certainly made a program twice as fast. Asymptotically, it is still linear. Right? It is still order of n time, but practically it is twice as fast. Right? Perfect. All right. So can we extend this? Can we extend this observation further? What about the third largest factor? What about the third largest factor? How large can that be? Well, if the number is divisible by 3, then the third largest factor can be up till n by 3, right? Does that make sense? So third largest factor has to be at max. It has to be less than or equal to n by 3. Similarly, the fourth largest factor has to be less than or equal to n by 4, right? And so on. So we see this pattern over here. Is that clear? Cool. Now the question is, we could use this particular observation to reduce our time complexity by half. How do we utilize all these observations? How do we really utilize all these observations? So to do this, let us make one more observation. Right? Let us actually go back to this observation that we had previously. Let us look at this thing once again. Okay. So let us say that instead of going from 1 all the way till 60, right? Instead of going from 1 all the way till 60, we only go till this midway point. Right? You clearly see that there is this midway point over here. After this midway point, so this is the midpoint. After this midpoint, the numbers will repeat. Yes, 6 into 10 repeats as 10 into 6. 5 into 12 will be repeated as 12 into 5, and so on. Right? So we only need to go till this particular point. We only need to consider this half. We do not need to consider the other half. All right. So if we are considering this half, then we have to go from 1 all the way till what number? We have to go from 1 all the way till this number. How do we find what this number is? How do we find what this number is? So basically, we are looking for a number I, right? We are looking for a number I such that I times something else. First of all, this should be equal to n, right? Because they are numbers, they are factors, right? So I times something should be equal to n. Secondly, I am looking for a number such that I is less than or equal to this something, right? Because so basically, I'm going till 6 because the pair of 6 or the number which is paired with 6 is greater than 6, right? 10 is greater than 6. If I go any higher, then the numbers will swap. 10 will now become, the first number will become greater than 6 now, right? So we are looking for a number over here that follows this property. Okay, so if this is x, then what can I say from here? I can say that x equals to n divided by I. Right, so I can put the value of x over here. I will get I is less than or equal to n divided by I. What can I get from this? I can move this I to the left hand side. Right, so I will get I squared is less than or equal to n. And what does this tell me? This tells me that these numbers, they must be less than or equal to. So I must be less than or equal to square root of n. Is this part clear? Is this derivation clear? This is very simple. A lot of you might already know this, but it is important from where this is derived. Right? This square root sign, this is not magic. All right. So once again, we are saying that we are looking for a number I, we are looking for a factor I, such that its paired factor, when we multiply them, we get n, right? They are factors. Now we are also saying that, okay, we are going to make sure that this factor must be less than equal to its pair. Right? This factor must be less than equal to its pair, because if it is greater than its pair, then we are just repeating ourselves, right? Because 2 times 3 is the same as 3 times 2. So we only need to make sure that this number is smaller than this number. Otherwise, we will be repeating ourselves. So we put this in the equation. We say I is less than equal to n by I, which means that I square is less than equal to n, which means that I is less than equal to square root of n. So what did we get from here? So now we can improve our program. We can now say that we have a for loop for I equals to 1, I less than square root of n, right? Square root of n and I plus plus. I less than equal to square root of n and I plus plus. Right? Now I will check if in fact n is divisible by I. So what should I print over here? If n is divisible by I should print I, right? I should print I. But is that all? Is that all? No, because I also have to print the other pair, right? Remember, we are only going from to half the pairs now. So we also have to print the other pair. So I will also print n divided by I, right? N divided by I, right? And that will complete the list of factors. Is this part clear? Yes. Perfect. Right. Now, first of all, there is a mistake in this program. There is a mistake in this program, a very subtle mistake. Can someone point that out? Yes. Exactly. So over here, let me just point it out. So over here, Lucky says that, hey, this is the mistake, right? What happens when I is actually equal to n by I? Which means that when n is a perfect square, you will be printing this number 2 times, right? That is not very good. You will be printing this 2 times. That is not very good. So how can we fix this? Right. So first of all, is everyone clear? If n is 9, n equals to 9, what we will see? We will see I equals to 1. We will print 1, 9. Right? I equals to 2. We will not print anything. I equals to 3. We will print 3, 3. Right? So we see that we printed 3 2 times. That is not a good thing to do. Right? So we need to resolve this. And we see that this only occurs when n is a perfect square. Right? Otherwise, this issue cannot occur. Right? So how do we resolve this? We simply say that I goes till less than square root of n. Right? I goes till less than square root of n. And after this, we will specially check. After this loop is over, we will check. So after this loop, what will be the value of I? It will be exactly square root of n, if it exists. Right? So we will say if n mod I equals to 0, then print it just once. Right? Print it just once because it is a square root. So just print I. Right? Notice that we are not printing the pair over here. Is that clear? Cool. So this will give us the correct answer. Now the question is, how much time did we save? What is the time complexity? What is the time complexity of this particular code? Yes. So who can tell me that? Well, this is very simple, right? Just like the previous case, we have a simple for loop. And this for loop now goes from 1 all the way till square root of n. So the time complexity is supposed to be order of square root of n. Right? Simple. Is that clear? There is one more thing over here, that if you were actually using a function to calculate the square root of n, you would not do this again and again. Right? You will actually say sqrt or square root equals to, you will calculate the square root of n outside. And then you will just use that variable, right? So that whenever you hit this condition, you don't have to calculate it again and again and again. Okay, so this will give us the correct code, and the complexity will be order of square root of n. Now that is a huge improvement, right? That is a huge improvement, going from order of n to order of square root n. This is huge. This is massive. Imagine that you had a number which was, let's say, 100 trillion, right? 100 trillion. If you 100 trillion is how much? 100 trillion is how much? It is 10 to the power 14. Right? If you were to check this number, if you were to check a number of this order of magnitude on your computer, it will take a lot of time. Right? How much time will it take? It will take around 10 to the power 5 seconds. Right? Or you can say it will take around 30 hours. It will take around 30 hours of time. Whereas with this particular algorithm, how much time will it take? It will take just 10 to the power 7 operations. So this is 10 to the power 7, square root of 10 to the power 14 is 10 to the power 7. So it will just take how much time? It will take 0.01 seconds. Right? That is amazing. We went from a program that took 30 hours to a program that ran in 1/100th of a second. All right? Cool. So this is how we would factorize a particular number. Okay. So I hope this is clear to everyone. Now let us move on to a question, right? To a question, related question. Okay. Suppose that we have 100 doors, right? And all these doors are closed. All are closed. So we have basically door number 1 over here, door 2, door 3, door 4, all the way till 98, 99, 100. Right? We have all these different doors, and initially all of them are closed. So let me say that these are closed. Okay. Now we are going to play a game. This game will have 100 steps because we have 100 doors. We will have 100 steps. So the first step, what will we do? We will toggle all the doors. Right? So you understand what toggle means, right? Toggle means that if it is open, you close it. On the other hand, if it is closed, you open it. Toggle basically means to flip it. Right? Cool. So we will say that in the first step, we will toggle all the doors. In the second step, we will toggle all the doors, all the even doors. Basically, we will toggle every second door. Every second door. Right? In the third step, we will toggle every third door. And so on and so forth. It will continue like this forever. In the 100th step, we will toggle. So there will be just 100, right? We will toggle the 100th door. Right? So this is what we are going to do. Is this part clear? So first of all, what happens after the first step? Initially, all of them are closed. After the first step, all of them will be open. Right? Then what will happen? After the second step, we will toggle this every second door once again. So this door will become closed. 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 Right? In the third step, we will once again toggle every third door. So this third door will become closed. There was a sixth door over here. Right? It was initially closed. So we will open it up. Right? And so on and so forth. Does that make sense? So we are doing this thing. That is the game we are playing. The question is that after we are done with this game, after 100 steps, which doors remain open? All right. Is the question clear? Yes, after the third step, we will toggle every fourth. So in the fourth step, we will toggle every fourth door. In the ith step, we will toggle every ith door. Right? And the question is, after all these 100 steps, which doors will remain open? Okay. All right. So, this 100 is a very, very large number, right? So let us actually reduce the problem. So whenever you have a difficult problem, you try to check that problem on smaller numbers, right? So let us say that we only have 10 doors. Okay, we only have 10 doors. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Initially, all of them are closed. Okay. What happens after the first step? So this is the 0th step. This is step 0. Step 1, step 2, step 3, step 4, 5, 6, 7, 8, 9, 10. Right? What happens after the first step? After the first step, every door is open. Right? After the second step, what happens? After the second step, what happens? So after the second step, 1 is open. 2 is closed, 3 is open, 4 is closed, 5 is open, 6 is closed, right? 7, 9, these are closed now. What happens in the third step? In the third step, 1, we do not change it. 2, we do not change it. 3 was open, right? 3 was open, so we will close it. 4, we do not touch it. 5, we do not touch it. 6 was closed, so we will open it. 7, we do not touch. 7 remains as it is. 8, we do not touch. 9 was open, so we will close it. 10, we do not touch. Yes? Okay, we move on. So in the fourth step, we will keep 1. We will not touch this. We will not touch this. This was closed, so we will open it. We will not touch this. We will not touch this. We will not touch this. This was closed, so we will open it. We will not touch this, and we will not touch this. And so on and so forth. So can someone see what is happening over here? Can someone see what is happening over here? Basically, what happens in the ith step? What happens in the ith step? Exactly. So Srinivas has the right idea over here. Srinivas says that in the ith step, all the doors that are divisible by I, get toggled. Right? That is the problem over here. Now the question is, let us suppose that I am talking about the nth door. Right? Let us suppose that I am talking about the nth door. For which all numbers, for which all steps will toggle this door? Will toggle this door. Right? So is the question clear? If in the ith step, I toggle every ith door, then given a door number, right? Given that, I am saying that, okay, let's talk about the 20th door. Right? Let's talk about the 20th door. Then in which all steps will this 20th door be toggled? In which all steps will this 20th door be toggled? All the factors of n. Exactly. Right? All the factors of n. Yes. So basically, 20th door will be toggled in the first step, in the second step, fourth step, fifth step, 10th, and 20th step. Is that clear? Yes, because these are all the factors of 20. Cool. So, how many times will this door be toggled? How many times will this door be toggled? Well, we already know that factors come in pairs. Right? Which means that if there is a step number 1 on which this is toggled, there is also a step number 20 on which there is toggled. Right? Similarly, for step number 2, we have step number 10. For step number 4, we have step number 5. Right? So we know that the nth door will be always toggled, an even number of times. Right? Because why is this true? Because the factors will come in pairs. Right? So every door is going to be toggled an even number of times. Is that correct? Well, not so fast. Is there any particular number which has an odd number of factors? Right? What happens? So you have this pairs coming up. Right? You have these pairs coming up. What if there is a middle value? What if n is a perfect square? In that case, this value root n, it doesn't have a pair. Right? Root n is going to pair with itself. So it will not have a pair. So basically, if the nth door, so if n is a perfect square, right? If n is perfect square, then nth door will be toggled an odd number of times. Right? In all other cases, it will be toggled an even number of times. Is that clear? Yes. All right. Cool. So what happens if you toggle a door even number of times? Initially, it was closed. Then it became open. Then it became closed. Then it became open. If we do this an even number of times, what will the end state be? It will be closed. Right? Because we started with closed, we toggled it even number of times. So eventually it will be closed. On the other hand, when n is a perfect square, we will toggle it odd number of times. So what will be the final state? We started with closed, we move to open, we move to close. Since we will do this odd number of times, the final state will be open. Right? So which all doors will be open? Now we know the answer. Which all doors will be open? All the doors whose numbers are perfect squares. Perfect squares, right? And all the doors from 1 to 100, which all doors are those? Which all doors are those? So that is 1. Then 4, 9, 16, 25, 36. Then what do we have? 49, 64, 81, and 100. Right? Exactly 10 doors will remain open, and all these are the doors that will remain open. Is that clear? No. If n is prime, the answer will be even. So Vishwajit has a question over here. Vishwajit says that if n is prime, then how many factors does it have? Well, for any prime number, it has two factors, right? 1 and n itself. So for prime numbers, it will be even, not odd. Only for perfect squares. Only for perfect squares will we have odd number of factors. Odd number of factors. All right? Cool. Okay. So what did we learn from this particular problem? This was not a very difficult problem, right? This also does not involve a lot of programming. We did not do anything fancy. We did not do any fancy maths over here. All we did was we sat down, we made some observations, right? We made some observations. We looked at the problem, we tried it with a smaller number. Instead of going to directly 100, we tried it with a smaller number. So that is something that you have to keep in mind, right? Whenever you're facing a problem, whenever you're facing an algorithmic problem or any problem in life, please, your first step should not be to come up with a solution. That is a very, very wrong way of doing things. The first step should be to make observations. Make observations. Right? Once you do this, only then you will be able to find a solution. Find a solution. If you do not make observations, you will never be able to find a solution. All right? So please do not skip this step. Okay. Cool. So that was a nice little exercise. Let us go back to what we were doing earlier. Right? So first of all, what we did was we found all the factors. Found all the factors of n. Right? That is the first thing that we did. Now, while we were doing this, we kept talking about something, right? We kept talking about prime numbers. So first of all, can someone quickly tell me what a prime number is? So what is the definition of a prime number? What is the definition of a prime number? A prime number, so first of all, it has to be a positive and it has to be an integer. Right? It has to be a positive integer. Secondly, it must have exactly two divisors. Right? It must have exactly two divisors. There is a lot of people think that this is the definition of prime numbers, right? A lot of people think that a prime number is a number which is divisible by 1 and itself. Right? By 1 and itself. If this was the definition of prime numbers, then 1 would be a prime number. Right? Then 1 would be a prime number because, hey, 1 is divisible by 1 and 1 is divisible by itself. But 1 is not a prime number. All right? Is that clear? So this is not the correct definition. This is very close, but this is not the correct definition. The correct definition is that it must have exactly two divisors. Exactly two distinct divisors. Right? So can someone very quickly tell me what the prime numbers are? A few prime numbers from the start. So is 0 prime? Is 0 prime? No, it is not. Is 1 prime? No, it is not. Is 2 prime? Yes, 2 is prime. 2 is the smallest prime number. Then 3 is prime. 4 is not prime. 5 is prime. 6 is not prime. 7 is prime. 8 is not prime. 9 is not prime. 10 is not prime. 11 is prime, and so on. Right? How many prime numbers are there? How many prime numbers are there? 100, 200, 500, 1000, million, billion. How many prime numbers are there? There are infinitely many prime numbers. Infinitely many prime numbers, right? Everyone knows this? Cool. There's a very simple proof for this as well. All right. Okay. So now that we know the definition of a prime number, some people are saying 4 prime numbers are there. That's nice. Suppose now that we know the definition of prime numbers, can we write a program? Can we check if a number is prime? Right? So we know that the definition of prime number is a number which has exactly 2 divisors and it is a positive integer. So given a number, can we check if it is prime? So is prime, right? It is going to return a boolean and it is going to take an integer. Yes. So how can we write this program? So very simple, right? Very simple. We can say that count is 0, right? We can write a loop for I equals to 1, I less than equal to n, I plus plus, right? And we can check if n mod I equals to 0, then we will do count plus plus, right? And finally we will return what? If the count is exactly equal to 2, then it is prime, otherwise it is not prime. Yes? Right? Cool. What is the time complexity of this program? What is the time complexity of this program? This program runs in order of n time. We already know that we can optimize this a lot. Right? We already know that we can So Suraj says why boolean? So this is prime will return true or false, right? It will return true or false. True if the number is prime, false if it is not. Right? Which is why we are returning a boolean. TechGeos is asking, sir, just confirming, is this code Java, right? So this might not exactly be Java. For example, in Java, you will have to put a semicolon over here, right? I'm not sure if you write bool or boolean in Java. I kind of forgot, but the rest of it pretty much looks like Java, right? Pretty much looks like Java if we add these semicolons. This will also work in C++, almost exactly the same way, right? However, when we are doing these classes, we will not be following any particular programming language. If you have any questions of a particular programming language, that let's say if you want to ask, okay, how will I do this in Rust, or how will I do this in Haskell, or how will I do this in, let's say, Python, right? So you feel free to ask that. Okay, feel free to ask that. I will be able to give you an answer for most common programming languages. However, we will not be focusing on the programming language in this particular class, right? We will be focusing on the pseudocode. We will be focusing on the intuition. Okay, cool. Okay, all right. So we see that this is linear in time, but we already know that we can improve this a lot, right? So how can we improve this? Instead of going from 1 to n, we can go from, so if 1 is a factor, right? If n is a factor, right? And prime numbers have exactly 2 factors. What does this mean? What does this mean? This means that if n is prime, if n is in fact prime, then it must not have any factor, between 2 all the way till n minus 1. Yes? Is that clear? It must not have any factor between 2 all the way till n minus 1. In fact, it must not have any factor between 2 all the way till n by 2. In fact, we can even generalize this and we can say that a prime number does not have any factors between 2 all the way till square root of n, right? Because we see that the factors will come in pairs. Right? The factors will come in pairs. Is that clear? So we can improve this code a lot. We can say boolean is prime, right? We have an integer n, and we will say, so now we don't need that count anymore, right? Because we are just checking if there is a prime factor or not, if there's a factor or not. So we can say for I goes from 2 all the way till square root of n, I plus plus, right? If there is any factor, if n mod I equals to 0, if we did find a factor, then what can we say? If we did find a factor, then what can we say? Hey, we found a factor, so it must not be prime. If you found a factor between 2 and square root of n, it cannot be prime. So we'll just return false. Return false over here. Right? And after this loop is done, we will return true. Because if we did not find any factors except for 1 and n, then the number must be prime. Is this clear? And the time complexity of this code is The time complexity of this code is order of square root of n. Right? Perfect. So we know that we can check if a number is prime in order of n time as well. Now, one question, it's not, I mean, we are not going to teach that today in the class, but one very common question is this the fastest we can do? Is this the fastest we can do? And the answer is no. The answer is no. In fact, primality testing, this is in P, right? This is in P. P stands for the polynomial time algorithms, right? I'm not sure if you have heard of P versus NP, right? But primality testing is in P. That means that we can check for primality in log n time, okay? In order of log n time. All right, we will not be going over this particular algorithm today. So there are several algorithms. One of the most famous ones is the AKS primality test, right? Okay, but primality can be checked in order of log n. It is in P, right? And no, this is different from Sieve of Eratosthenes. Right? This is different from the Sieve algorithm. This is a different thing. Okay. So if someone asks you how much time does it take to check if a number is prime, the answer is log n. Right? You can test primality in polynomial time. Okay. Cool. Vikas says, what if n equals to 5? So Vikas has a question over here. Let us look at this code and see what happens when n equals to 5. Does this code work correctly? Right. So let us try that. So what happens? So first of all, we will say I equals to 2. Right. So we will first come over here. We will check I equals to 2. Then we will move on to the condition. We will move on to this condition. Right. That is how a for loop works. We initialize, we check the condition, we go inside the block, we increment, and we check the condition again. Right? So we will check this condition. Well, what is the square root of 5? The square root of 5 is, well, the square root of 5 is 2 point something, right? Let us suppose that we are doing integer things over here. So we will say that, okay, this is 2 is less than equal to 2.5, right? Less than equal to 2 point something. So we will go inside, right? We will go inside. We will check, is n divisible by 2? Is 5 divisible by 2? No, it is not. Right? So we will continue the loop. We will increment I. I will now become 3. Now once again we will check, is 3 less than equal to square root of n? No, 3 is not less than equal to square root of n, right? 3 is greater than square root of n. So we will exit this loop and we will return true. So we will say that yes, 5 is prime, which is correct. Okay. Okay, so there's another question. Santosh says that, okay, what if 2? What if we check with n equals to 2? Right? What happens when n equals to 2? Won't this program return false? Let us see, right? So when n equals to 2, we start, right? We start with I equals to 2. Right? Then we move on to the condition. We check if 2 is less than equal to square root of 2. Is this true? Is 2 less than equal to square root of 2? No, it is not true. Right? This is not true. So it will directly come outside the loop. Okay, it will directly jump outside the loop. It will not go in the loop. And we will return true. So even for true, we will return true. Is that clear, Santosh? Yes. But this program is not 100% correct. This program is not 100% correct. Can you tell me one value for which this program will fail? Exactly. So Ayush has the right idea over here. What if n equals to 1? Or what if n equals to 0? Or what if n equals to minus 100? Right? For all the numbers that are less than 2, we will never go inside this loop. So we will automatically return true. Right? So we need to improve on this program. We need to add a check over here. Right? So let me just insert some space. So we will very quickly, let me just clear up the mess. This was square root of n. So we will add a check over here. We will check if n is less than or equal to 1, then we simply return false. Right? We simply return false. All right? Is this clear? No, this is not a base case. Base case happens when you are in a recursion. Right? Base case, we talk about base cases when we are in a recursion. This is a edge case. This is a boundary condition. Okay? Sujit, it's almost the same, but it is better if we follow the correct nomenclature. Okay? Base case is when we talk about recursion. Currently, we're talking about edge cases or boundary condition. All right. Yes, we can also say that this is less than 2. Right? We can, instead of saying less than equal to 1, we can also say less than 2. That is perfectly fine. All right. Okay. Let us continue. So now we know how to check if a number is prime. Now a very common question comes up. Let me just check how we are doing on time. All right. So a very common question comes up now, which is called if you had to find all the primes till n. Right? So I give you a very, very large number n, let us say 1 million. Right? And I ask you, find out all the primes till 1 million. Right? How will we do that? Is the question clear? We have to find all the primes till 1 million or some number n. So one way of doing that is to very simply go through all the numbers and check if they are prime. Right? So we can simply do for I equals to 1, I less than equal to n, I plus plus, right? And we will say if is prime. If is prime of I, right? So this is prime is the function that we have coded earlier. This is prime is the function that we have coded earlier. We will simply print I. Simple enough? Yes. How much time will this algorithm take? How much time will this algorithm take? Well, this is prime function. This takes order of square root of I. Right? This takes order of square root of I. And we are doing this thing n times. Right? We are doing this thing n times. So how much time does it take? It definitely takes, it is bounded by, it is upper bounded by, so the time complexity of this program is upper bounded by order of n times square root of n. Right? N times square root of n. It is a little lesser than that, but as importantly, this is what the type bound is. Okay? Cool. Can we do better? Now the question is, can we do better? This was the simple approach. We had the program, we had this function is prime that we have already coded, right? And we simply say, okay, let us go through all the numbers and let us check them. So this will take this much time. The question is, can we do better? All right? Cool. So the answer to this is yes, right? In general, yes. There is something called Sieve algorithms. Sieve algorithms. All right, and there's a lot of different sieve algorithms. So one of the most famous that you will come across is the sieve of Eratosthenes, right? The sieve of Eratosthenes, and this is how you pronounce the name. You say Eratosthenes, okay? Eratosthenes. So this sieve algorithm can achieve much better time complexity. All right. Now let us continue this particular thing in tomorrow's class. All right, we are going to keep the today's class simple enough because you will have a lot of practice problems that you can go and try. We will talk about this sieve algorithm tomorrow, and this is a very elegant algorithm. This is a very nice algorithm. It is also very simple to code, right? So it only has like 5 to 6 lines of code, and that gives you a very powerful algorithm that checks, that finds all the numbers, all the prime numbers of a given number. All right, cool. So one thing that Ankush is pointing out over here, or not this, where did that comment go? Interesting. That comment just vanished. Yes. So Ankush is pointing out over here that in this particular program that you wrote, right? In this particular program that you wrote this loop as I equals to 2 all the way till square root of n. We can rewrite this in this manner as well, right? So I'm just pointing it out over here, as Ankush said, that these two loops are equivalent. I equals to 2, I is less than equal to square root of n, right? I plus plus. This loop is the exact same as this loop for I equals to 2. I times I is less than equal to n, I plus plus. Okay, so instead of calculating the square root of n and then comparing it with I, we square I and then we compare it with n. Right? It will work exactly the same. And this is one more way that you can do it. If you were to do it this way, then you will have to pre-calculate the square root of n, right? You will say square root of n equals to, you will use some sort of a math library. You will say math.square root of n and things like that. So if you do not want to do that, you can simply use I into I is less than equal to n. All right? Bridge says, but don't we have to check for overflow? Well, not really, Bridge, because I into I will not overflow, right? If I into I overflows, then N itself should overflow. Does that make sense? We are not really considering the overflow case over here. We're talking about not too big numbers. Okay, we are talking about numbers that will fit in the integers. Now, if n fits in your memory, if n fits in let's say a 64-bit integer, then I into I will also fit in 64-bit integer. All right. Srinivas says, sir, how to deal with very, very big numbers? Well, Srinivas, there are a lot of different ways that you can tackle big numbers. One very common approach is to use a big integer library, right? Big integer library, right? But usually, this is not a very good approach, right? First of all, the question is, why would you need to deal with big numbers? Right? If you are implementing, let us suppose, some sort of an RSA algorithm, and you want to check if a number is prime or not, then you might have other ways of generating large prime numbers. Right? In practice, we don't really have to deal with we don't have to check very large prime numbers with something like a sieve. Right? With something like a sieve, we don't do that. Okay. So let us end the class. Once again, please subscribe to the channel, hit the bell icon so that you can be notified of the videos. And in the next class itself, we will be going over prime numbers once again, and we will be going over a lot of different things. So we have to cover GCD, so greatest common divisor, Euclid's algorithm for that. We have to cover model arithmetic and a lot of different topics. All right. So please make sure that you subscribe to the channel, hit the bell icon, and please go and practice the problems.
Hello everyone. So in the last class, Pragya has taught you about how to check whether a number is prime or not. Okay, so is everyone clear with that? If given a number n, can you all check whether the number is prime or not? Now, once you know that whether a number is prime or not, now let's try to modify the problem a bit. Okay, so instead of getting a direct problem of checking whether a given number is prime or not, let's say that you have to print first n prime numbers. Okay, given a number n, you have to print the first n prime numbers. Or another question could be that you have to print all the prime numbers less than n. Another question would be that you have to print all the prime numbers in the range from L to R. Okay, so these are the three types of questions which we are going to solve optimally in today's class. Okay, now if you all remember, if when you have to check whether a given number is prime or not, what is the time complexity of that operation? You are going to run a loop that starts from 2, goes till square root n, right? And with every number in this range, you try to divide n, and you see whether n is divisible by that number or not. If n is divisible by none of the numbers, then you can say that n is prime. So the time complexity of this operation is order square root n, right? Now, if you have to check, if you have to print the first n prime numbers, what will be the time complexity of this approach? If you have to print first n prime numbers, you will be checking for all the possible numbers, right? You will run a loop for all numbers from 1 to n, and then you will run another loop. Maybe you will have to increase the size of the first loop because first n prime numbers might exceed n as well, right? So the time complexity of this is going to be n root n, right? For each and every number, you will be checking, you will be running a square root n check, right? Similarly, if you have to print all the prime numbers which are less than n, again, the same time complexity will be there, n root n. If you have to print all the prime numbers in the range from L to R, then again, size of range multiplied by square root n. So all these types of questions can be solved in this time complexity n into square root n using a very easy check prime algorithm that we have learned in the previous class. Okay, can we do it optimally? Can we do something to make all these problems easy for the computer? Now, there is a very, very well researched algorithm, with very famous algorithm, which many of you are already writing in the comment. It's called the Sieve's algorithm, right? So in today's class, we are going to learn about the Sieve's algorithm. Okay. Do you guys understand what is a sieve? What is the literal meaning of a sieve? If you just translate sieve in Hindi, what is that? It is nothing but a channi, right? This is chai chante hain ghar pe. So it has a net, very fine net, and a handle, right? This is a sieve, right? And printing all the prime numbers using a sieve is going to be exactly same as how you filter your tea. Okay, we'll see how. So जब चाय छानते हैं तब क्या होता है? You have a utensil, right? In this utensil you have the cooked chai, right? And then you pour it on the sieves, and after this you have your tea mug, right? So At this point, this complete mixture is called chai, right? At this point, you say that everything which is there in the utensil is my chai. But when it is filtered, then whatever is in your teacup is called chai, right? तो पहले तो जो उसमें था पूरे को हमने बोल दिया कि यार ये चाय है, चाय बन गई है, इसको छान लेते हैं. जब छन के आई तो फिर हमने बोला यार चाय तो ये है, ये जो इसमें रह गया है ये चाय नहीं है, ये चाय पत्ती है, अदरक है, जो भी है, चाय नहीं है ना. So Sieves is going to function in an exact same way. We have to figure out what are the prime numbers. We'll say that all the numbers are prime, right? So we'll take all the numbers and we'll say that all of them are prime. Then we will pass them through a Sieves. After passing them through the Sieves, we will see that only the actual prime numbers are remaining. All the composite numbers will be filtered out by the Sieves. Okay. Let us see how it is going to work. So first of all, let us write down all the numbers on which we'll be running the Sieves. Okay, so we have all these numbers. Initially, just like the T, I'm saying that all of them are prime. Okay, all the numbers are prime. Now, for 1, we are very sure that 1 is not a prime, right? Is everyone clear with this thing that 1 is not a prime, right? Why is 1 not a prime? Because a prime number has to have exactly 2 divisors. 1 has got only exactly 1 divisor, so 1 is not a prime, so we can directly remove 1. Okay. Now, whatever is the first number which is present in this in the list of all these numbers, which is available in the list, we'll say that this number is a prime number. Okay. So what is the first available number here? The first available number is 2. So I'm saying that 2 is a prime number. So we'll filter out 2. 2 comes out of the Sieves. Okay. So we have poured all the numbers here till 40, and now 2 has fallen. 2 has been successfully, he has crossed the Sieves. Okay, 1 has stuck here. Now, if 2 is a prime number, can I say that all the multiples of 2 will never be a prime number, right? Because all the multiples of 2 will definitely have 1 as a divisor, themselves as the divisor, and also 2 as a divisor. So they are not satisfying the criteria of being a prime number. Does this thing make sense to everyone? Does this thing sounds obvious to everyone? That any multiple of 2 can never be a prime number, right? So if any multiple of 2 can never be a prime number, so what can we do? Filter them out, cut them. So I will just cut all the multiples of 2 which are present in this list. So 4 is gone, 6 is gone, 8 is gone, 10 is gone, right? So all these multiples are removed from this list. These all have been filtered out and thrown away. What is the next available number which is there in the Sieves? What is the next number that I can see? The next number is 3. So I can say that, okay, 3 is also a prime number. Let's add 3 as well. Okay. Once I am declaring that 3 is a prime number, can I say that any multiple of 3 does not stand a chance for being a prime number? Any multiple of 3 is always and always going to be a composite number, right? So let us filter them out. Let us remove them from the list. So let us remove all the multiples of 3. 6 has already been removed. Then we remove 9. 12 has already been removed. We remove 15. 18 is already gone, right? And then 21. 24 is gone. 27. And then 33. 36 is already gone. Then 39. Okay. Now, which number is the next available number in this list? The next available number is 5, right? So I can say that 5 is also a prime number. Okay. So out of all these numbers, we have till now filtered out 3 numbers which are prime numbers, right? So now 5 has come. So any multiple of 5 will never be a prime number. So all the multiples of 5 will also be removed. So currently I can see that all the multiples of 5 have already been removed. 10 is gone, 15 is gone, 20 is already gone, 25 is remaining. So we'll remove 25 as well, and then 35. Okay. Then what is the next available number in this list? The next available number here is 7. So 7 becomes the next prime number. Okay. And all the multiples of 7 will also be removed. So now 14 is gone, 21 is gone, 28 is gone. All the multiples of 7 have already been removed. Okay. What is the next available number that we have? Now we have 11. So 11 becomes the next prime number. And all the multiples of 11 again have already been removed. Then we have 13. Then we have 17. Then we have 19. Then we have 23. Then we have 29. Then we have 31, 37. And that's it. So now you can see that we have got all the prime numbers in the range from 1 to 40. These are all the prime numbers in the range. All the prime numbers which are less than 40 are now with us. Is the idea of the algorithm make sense to everyone? Is the idea clear? How the algorithm is going to work? initially we said that all the numbers are prime numbers, assume that all of them are prime numbers, pass them through the sieves. What does the sieve do for us? The sieves algorithm takes the first available number and declares it a prime number. So we declared that 2 is a prime number. Since 2 is prime number, none of its multiple can be a prime number. Cut them out, remove them. Then take whichever is the next available number, call it a prime number, remove all the multiples of this number as well. Okay. Now let's try to see how can we write the code for this. Okay, the code is going to be very, very small, very, very easy, right? So what we are doing here is initially what we are doing is we said that let us first take all the numbers. So if let's say we have to print all the prime numbers in the range n, so then we take an array prime of size n plus 1, because if n is 40, array indices are going to start from 0. So I also need 40 as an index. So I will take the size as n plus 1. Okay, and I will say that all of them are prime. Okay, so this primary, what does it hold? This primary, for every index, it holds true or false based on whether the number is prime or not, right? So currently I'm saying that if this is my array, okay, currently I'm saying that all of them are prime. So have true for each and every index. Okay, then what we will do is we'll first declare some of the already known values, right? So we know that 0 is not a prime, so we can say that prime of 0 is false. So this will be turned false. And we also know that prime of 1 is also not a prime, right? So 1 will also be converted to false. Now starting from 2 to n, we have to check each and every number whether they are prime or not. So how did we do this in this algorithm? We selected whichever is the first true value. Basically, the first available means the first true value, which is currently declared as a prime number, right? So we'll run a loop which will start from 2, and this loop will go till till n, and we'll be incrementing the value of I one by one. And then we have to check whether this value has been removed or not. So if it has not been removed, then we will always be having a true value. Okay, so we'll just check if this number at index I, if it is true, if this number is currently a prime or not. What is the first available prime number that we have here, right? If it is a prime number, this means that none of its multiple can be a prime number. So for all its multiple, make them false. So if 2 is true, 4, 6, 8, 10, all these numbers should be turned to false. So I will just run a loop. Let's take a different variable. So now what we have to do for I, we have to make 2i, 3i, 4i, all these numbers as false, right? So we'll quickly run a loop starting from 2, and we'll see till where we have to run this loop, and then do this. We'll say prime of I into j, right? So I is already there. This is our j, right? This has to be false. So we till what value we have to increase j? We don't know, right? We don't know that. So we actually don't know till when we should be incrementing j. But what we know is that this product, this 3i, 4i or ji, this can never be greater than the maximum value that we have. So this product can never be greater than n. This always has to be less than or equal to n, right? So here what we'll have is j into I is less than or equal to n. Okay, because if you see in this list, when you select I is equal to 2, then from where to where your j ranges, j starts from 2. So if j is equal to 2, you cut 4, then j becomes 3, you cut 6, j becomes 4, you cut 8, and you will go till 40, right? So j becomes 20. You don't want to increase j such that you are trying to cut a number which is greater than 40. So always we are keeping I into j less than or equal to n. Okay, cool. Now let us see. Let us try to quickly see what happens when we are actually cutting the numbers, right? So when my I takes a value 11, okay, when I'm taking a value 11, in this case, when we selected 11, what was the first number that we tried to cut? The first number that we tried to cut was 11 into 2, which is 22, right? So if I is 11, we are going to check it for value of j is equal to 2, right? Which will give us 22. Then we will try to cut 33. Then we will try to cut 44. Then we will try to cut 55 and so on. Then j will become 11 and we will cut 121 and so on, right? Now I have a question. When I'm trying to cut all these numbers for the value of I equals to 11, can I say that 22, 33, 44, 55, all these numbers would have already been cut? Because before I takes the value 11, I will also take the value 2. When I takes the value 2, 22 would have been cut by that, right? So you must have observed in this case also that when we reach to 11, all the multiples of 11 were already cut, right? When we reached to 5, what was the first number that we cut? 10 was already gone using 2. 15 was already gone using 3. 20 was already gone using 2. What was the first number that we cut using 5? It was 25. If I start from 11, then we can see that none of the multiple of 11 is available here, which has not been cut. All the numbers have been already cut, right? Why that happened? Because before taking a value 11, I must have taken all the values which are less than 11. So all those values have already been cut. So 22 has been cut by 2, 33 has been cut by 3, 44 has already been cut by 2, 55 has been cut by 5, and so on, right? So what should be the first value from where we should be starting the second loop? From where we should start the second loop? This has to start from j is equal to I, right? Because when we were trying to cut the numbers from 5, we saw that the first number that we are cutting is 25. Similarly, for 11, the first number which will be available there is going to be 121. All the other numbers must have been cut by the smaller values of I. So we don't need to start from 2, we can start j from I, okay? Now, if we are starting j from I, what is the maximum value that I can take? Do we need to run the first loop till n? Okay, let us try to analyze the second loop, and that will give you the answer whether we should be running the first loop till n or not. Should it go till n by 2? So what is the maximum value that we have to cut? The maximum value that we have to cut is here 40, right? Okay, and whenever you are starting to cut, you are always starting from the I value, which means that the first value that you are cutting is I square, right? For 2, you are cutting, the first value that is being cut is 4, right? For 3, the first value that you are cutting is 9. For 5, the first value that you are cutting is 25. For 6, the first value that you will be cutting is, for 6, you will anyhow won't cut any value. For 7, what will be the first value that you will be cutting? For 7, the first value should be 49. 7 into 7 is 49. Is 49 in this range? No, 49 is out of this range. So what should be the maximum value? The maximum value till which we can go is I square. So I can never go beyond square root n, right? Because the first number that you are cutting here, like this number, which is the last number, would have been cut when I becomes square root n, right? So this n can be turned to square root n. Right, so either you can say I is less than equal to square root n, but if you are using this function square root n, this is an expensive operation of finding a square root of a number is actually an expensive operation. It will take at least log n time. So what you can do is you can replace this by I into I less than equal to n. So now you are doing the checking order 1 operation. This is going to take log n time, at least if you are printing the integer part, right, using binary search. Okay, so now let us come to the time complexity. Okay, this loop, the first loop is running from 2 to square root of n. Let us actually remove all the optimizations that we have done. We'll try to calculate a very relaxed upper bound. Okay, so tell me one thing: when the value of I is equal to 2, how many times does the inner loop run? If let us say that this starts from 2, if we are considering the previous loop, the totally unoptimized loop, which was starting from 2 and going till n, and this loop is also going till n, we are considering the most unoptimized version. Now tell me, if value of I is equal to 2, how many times are we going to run this loop? This loop will start from 2, go till n by 2, right? We'll be cutting exactly n by 2 numbers. For I is equal to 3, how many times is the inner loop going to run? The inner loop is going to run for n by 3 times. For I equals to 4, how many times is the inner loop going to run? For I equals to 4, is it going to run? Is it going to run for n by 4 times? For I equals to 4. So see what happens is when I takes a value 2, we cut 4. We say that now 4 is not a prime because 4 is a multiple of 2. And before running this loop, we are always checking whether I is prime or not. Is 4 a prime? No, 4 is not a prime. So this loop, the inner loop is going to run how many times? Exactly 0 times. This if case is going to fail for 4, right? For 5, it is going to run for n by 5 times. For 6, this is going to run for, again, 0 times. 6 is not a prime. For 7, this is going to run for n by 7 times, right? So can you see a pattern here? If we have to add all these time complexities, what will we get? We'll be getting n by 2 plus n by 3 plus n by 5 plus n by 7 and so on. What are these? If you take n common from here, you get 1 by 2 plus 1 by 3 plus 1 by 5 plus 1 by 7 plus 1 by 11 plus 1 by 13 and so on. What are all these? These are nothing but sum of reciprocals of prime numbers, right? First n prime numbers basically, correct? So I can say this is equal to I equals to 1 to n 1 by p. All the prime numbers, the first n prime numbers, or maybe all the prime numbers which are less than n, right? All the prime numbers which are less than n. This is the time complexity. Now, if you are really good at mathematics, you will be able to you will be knowing that this whole sum can be approximated to log of n. Okay, so this is the overall time complexity of Sieve's algorithm. Okay, so if you are really good or if you are interested in mathematics, you can read about the Merton's theorem, which proves this thing. Okay, that sum of reciprocal of first n prime numbers is same as log of n. So the overall time complexity can be approximated as order of n into log of n. Okay. Okay, I will quickly brief over the time complexity part once again. Okay, so if we are just checking for every value of I, how many times is the inner loop going to run? Okay, so I said that if I is equal to 2, how many times is the inner loop going to run? Inner loop is going to start from 2. We are assuming the most unoptimized version. We are removing all the optimizations that we had done. So inner loop will start from 2 and it will run for n by 2 times, right? If you are starting from 2 and you have to go till 40, you will be running 20 times, right? You will cut 20 numbers in this loop. Similarly, for I equals to 3, you will be running the inner loop for n by 3 times. For I equals to 4, now this is a very important thing that before running the inner loop, you always check whether this number is prime or not. 4 is not a prime. So for 4, the inner loop will never run. For I equals to 5, the loop runs for n by 2, n by 5. Then for 6, again, since 6 is composite, loop does not run. Then for I equals to 7, loop runs for n by 7, and so on. So if you add all of them, right, because then you have to calculate the time complexity, you will be adding how many times the inner loop is running in total, right? And that will be the overall time complexity. So if you add all of them, you get this series. Here, if you take n common, then you get something which is nothing but the sum of reciprocal of all the prime numbers. And if you apply Merton's theorem, if you are aware about the Merton's theorem, you will be knowing that sum of reciprocal of all the prime numbers can be approximated as log of n. So that is why the time complexity of Sieve's algorithm is order of n log of n. Okay. Now this is the most relaxed time complexity that we have achieved because we removed all the optimizations, right? The optimization that says that the first loop should run only till square root of time. This loop should start from I. We have removed all of them and then we have calculated. So whatever, if you do any optimization here, your algo is definitely going to be better than this time complexity. Okay. The question is, will this work for a range whose first element is not a prime number? This is only going to work if you are starting it from 2. If you are starting from any random number, this algorithm is never going to work, right? Because you have to make sure that all the composite numbers are cut. So if let's say if you are trying to find the numbers in the range from 40 to 100, right? So you have these numbers, and now if you start cutting the numbers from 40. You're trying to cut the multiples of 40. This is not what Sieves is suggesting. Sieves is saying, give me the first prime number. What is the first prime number? First prime number is 2. Cut all the multiples of the first prime number, not the first prime number in this range. The first prime number overall, right? So you will always be starting, or this algorithm will only work if you are starting cutting the numbers from 2. However, if you have to find the numbers in a range, what you can do is you can pre-compute all the prime numbers. So what you can do is, if you have what would be the maximum value of range, then starting from 2 to that range, you can pre-compute all the prime numbers. Okay. Once you have all the prime numbers in this range, now what you can do is you can this array is going to be a sorted array, so you can apply binary search and you can find all the positions of the lth prime number and rth prime number and print all the values. Okay. Cool. Is the Sieves algorithm clear to everyone, including the idea, the intuition, and the code? Is everything clear to everyone? Great. Now what we'll do is we'll try to see a problem. Okay. So we still have 30 minutes. So we'll try to solve a very, very good problem, which is a very commonly asked problem and a very generic problem. Okay. The problem says that given a number, return the prime factorization of this number. What is prime factorization? So is everyone here clear with the thing that any composite number can be written as the multiple of all prime numbers? Not all prime numbers, but multiple of prime numbers. Is everyone clear with this thing? So if I give you n is equal to 24, what would be the prime factorization of 24? 24 can be written as 2 into 2 into 2 into 3. Basically 8 3s are 24, right? So 8 is nothing but 2 raised to power 3. So 24 can be written as this. So the prime factorization of 24 would be 2, 2, 2, and 3. This is what you have to return. Okay, is the problem clear to everyone? If the value of n, let's say, is 10, you will be returning 2 into 5. Okay. If the value of n, let's say, is 42, then we have 2, 3, and 7. Okay. Is the problem clear to everyone? Given a number n, you have to return the prime factorization of n. Prime factorization means you have to represent that number in terms of only prime numbers, and that is possible for each and every number, right? Because any number either will be a prime number or a composite number. If it is a composite number, you can further divide it into prime numbers, right? For example, if n is 24, you can write it as 2 to 2 into 3. There can be many ways. Can there be many ways? Varun, just try to think and figure out. Can there be many ways? If you are breaking down the number into prime numbers, not composite number, none of the numbers in the returned array should be a composite number. Okay, what can be? What is the first thing that comes to the mind? So if, let's say, I'm given 24 and I have to, so we must have done this in schools, right? We all have done the prime factorization of the number in school in the elementary mathematics, right? This was, I think, in 6th class maybe, or 5th class, when we learned about the prime numbers, right? So how did we used to do it at that time? So if I'm given 24, what will I try to do? I will pick what is the smallest number with which I can divide it, right? So the smallest number that I can figure out is 2. So I will try to divide 24 with 2. I get 12, okay? And this 2 gets added to my answer. Now I have got 12, and I know that again I have to do the exact same thing. Find the smallest number with which I can divide this, and that number obviously should be greater than 1, right? So again, here also the smallest number that I can think of is 2. So I divide it with 2, I get 6. Again, I can divide it with 2, so I get 3. Now 3, the smallest number that can divide 3, bigger than 1 is 3, so I get finally 1. All these numbers are definitely going to be a prime number, because we are always selecting the smallest number, right? If that smallest number is not a prime number, then there must be a number which is smaller than this that can divide this number. Does this make sense to everyone? What I'm trying to say is, if there is a number x, which is the smallest number, which is dividing 24, and x is not a prime number. If it is not a prime number, then it must be a composite number, and then it can be broken down into 2 prime numbers at least, right? So 24 will also be divisible by these two. So that means x was not the smallest number that can divide it. There are smaller number than x which can divide 24. So using this proof by contradiction, I can always say that the smallest number which is able to divide any number is going to be a prime number. Okay. Now, how to code this thing? I'm just going to code the same approach that we used in our 5th, 6th class mathematics, right? So to do this, first we can initialize an answer array or maybe a prime factor array. And what we are going to do is, so here in this case, I just used my mind and saw that this is divisible by 2. But for computer, we'll have to check with every number starting from 2, right? What is the first number that divides 24? And then keep dividing it by that number till it is divisible, right? So I will start from 2 and I will say that this has to go till somewhere and then I plus plus. And then I will say while this is divisible, if it is not divisible, then it will not go inside the loop. But if it is divisible, first of all, add this I to the answer. So we'll do prime fact dot add I. Okay. Add this to the answer and then divide n. So n will become n by I. Okay. So what we are doing in this case is n is initially 24, right? We are starting from I, and we are and the first value of I is 2. So we are checking if it is divisible. If it is divisible, then keep dividing it till it is divisible. So we divide it, make it 12, n becomes 12. Then the loop still checks that this is still divisible by 2. So keep dividing it, and also keep adding it to the answer. So the answer will have 2, then in the next step again 2, and then again 2. Then you have 3. So this will break out because now n mod 3 is not divisible. Sorry, n mod 2 is not divisible. N has now become 3, right? 3 mod 2 is not equal to 0. So we'll increment the value of I. So I now becomes 3. So then we'll check n mod 3 is now divisible. So we'll add 3 to this and we'll divide n further. So now n becomes 1. Okay. So the question is, till when this loop should run? What should be the breaking condition here? What can be the maximum number that I can take? The maximum number that I can take is, we may use set instead of array. No, you cannot take set because set will guarantee that the occurrence of every number will be limited to exactly once, whereas we need 3 2s. If you are taking a set, you will have exactly 1 2, right? So set is not useful in this case. We'll have to take a list, array list, or array which supports multiple occurrences of same character, right? Okay, so what should be the maximum value that I can take? The maximum value that I can take obviously is going to be square root of n, right? So the I that we are going to increment is going to be till square root of n. Okay. Now this code is going to print all the prime factors for us. I can see that there are 2 mistakes in this code, 2 very big mistakes. Can you guys quickly figure out them? This code has 2 blunders, and one of them is the most commonly done mistake while writing a code. Even when people write the most simplest of the codes, they make this type of mistakes. Can you quickly figure that out? It doesn't work for 0 and 1. Yes, so this is guaranteed in the input that n will always be greater than 1, because even the person who is asking the question knows that 0 and 1 will not be are not eligible for this question. Okay, right. So I can see that one of the mistake has been pointed out. The other mistake no one is able to guess. Let us see what we are doing. Let us quickly reiterate over the code. We are saying that I is starting from 2. I should go. What is the maximum limit that I is taking? It is taking square root of n. So here, instead of this, I would be writing what? Actually square root of n, or maybe to keep it optimized, let us have I into I less than equal to n, right? This is the more optimized version of the same thing. Okay. So what we are doing here is we are initializing I. We are checking that I should not go more than square root of n. And inside this loop, what we are doing is we are changing the value of n, correct? N is changed inside this loop. N is also there in the breaking condition. So initially we started this loop with an assumption that n is going to be 24. So the maximum value that I can take is going to be root 24. In the next iteration, you changed n to 12. So this loop here, now this condition is not going to hold true because n has been changed. This is the most common mistake that I have seen students doing while writing most easiest of the codes. If you are changing a value inside the loop, you should never be taking it in the breaking condition. So always do one thing, assign some variable this value and then use it here. Okay, otherwise you will see your code behaving in very unexpected way and you will not be able to realize what is going wrong there. Okay, so assign the value and then keep it inside the loop. This is one mistake. What is this other mistake? The other mistake most of you have already pointed out, which is if the number is already prime, right? If the number is already prime, or maybe number is having the number is having a prime factor which is greater than square root of n, right? If a number is having a prime factor which is greater than square root of n, for example, let us talk about 404. Okay, so for 404, how will this loop run? We'll start from 2. We check that 404 is divisible by 2. We divide it. Okay. Then we again check that this is again divisible by 2. We divide it. Now this is not. So we have added 2 and 2 in the array. Now this is not divisible by 2. Then this is not divisible by 3. And what would be the maximum value of that I will be taking in case of 404? The maximum value that I can take is going to be 20, right? Because the square of 21 is going to be greater than 404, right? So the maximum value of I is going to be 20, but we can see that for all these values of I, the prime factorization of 404 is not complete, right? So what we can say in this case, right? Because this is not complete. 101 would also have been there, correct? So this is another mistake in this code. How to fix that mistake? Can I say that even after removing all the possible prime factors from that number, if I have got a number which is greater than 1, that number must be a prime number. Can I say this? So to actually fix this code, can I just add another if condition? It says that if this number is still not reduced to 1, that means that this number has to be a prime number. So directly add this remaining number as well. So what we'll do here is if n greater than 1, then prime factor dot add n. We'll add this line here itself after the for loop completes. So if this number is not been reduced to 1, we will add 101 as well, and we will get the correct answer. Does this make sense to everyone? So this is about prime factorization. What is going to be the time complexity here? What is the time complexity of this code? So calculating the time complexity is pretty easy here, right? The first loop runs for how many times? The first loop runs for root n time. Okay. Then the second loop runs for, the second loop is going to run for how many times? We are dividing the number n by I every time in every iteration. So how many times the second loop is going to run? The second loop is going to run for log n time. So what should be the time complexity? Is it going to be root n into log n? Is the time complexity going to be root n into log n? No, right? This is wrong. This is not going to be root n multiplied by log n. Okay, why? We can quickly see that this loop runs for root n times, and here we are dividing the number by I every time. In the worst case, the value of I is going to be 2. So in the worst case, if you are dividing n by I, how many times can you divide it? If given a number, how many times can you divide that by 2? This is given by log, right? This is given by log of 16. Log, whatever is the value of log of 16, you can divide 16 that many times by 2, right? But this is incorrect. Why? So let us try to analyze what is going on here. So if we have a value, let's take 16 itself. Okay, so in the first iteration, when the value of I is equal to 2, we check that this is divisible and we divide it. So we get 8. Then again we divide it by 2, we get 4. Again we divide it by 2, we get 2. Again we divide it by 2, we get 1. Okay. Now after we have divided completely with 2, for the next value of I, which is equal to 3, how many times is the inner loop going to run? For 3, how many times is the inner loop going to run? 0 times, right? Inner loop is not going to run because this has already been reduced to 1. Okay. If this has already been reduced to 1, now this inner loop will never run again. If this inner loop is not going to run again, for 3, number of iterations are going to be 0. For 4, the number of iterations are going to be 0, right? So what is the total number of times, including all i's, the inner loop is running? For all the i's, the inner loop is going to run for log n time. This is not for each and every I. This is for all the i's combined. For 2, it runs for log base 2n. Then for 3, it runs for log base 3n if n is there, right? So if let us talk about any other number. So if I talk about 24, 2 can reduce it to 12, then 2 can reduce it to 6, then 2 can reduce it to 3. Now 3 is not going to have log base 3 24, these many steps, because 3 is going to reduce this number, which has already been reduced by 2, right? So the total number of steps, including all the i's combined, is going to be log of n. So this is going to be log of n plus square root of n, which is nothing but square root of n. So the time complexity of this algorithm is going to be exactly square root of n, not root n log n. Okay. Guys, in mathematics, there are multiple topics which are very, very important for programming point of view, or both the interview point of view as well, right? So there is modular arithmetic that you must learn, and you must solve multiple problems on this. Okay. Then there is GCD, the LCM, and HCF problems. Okay, GCD is also very, very important concept. Okay. Then of course you definitely have the prime numbers, and in the prime numbers you can also optimize this approach that we have discussed, right? You can optimize this approach using a concept called the smallest prime factor of a number, which is called the SPF, which we haven't discussed in the class, but this is also a very important concept. Okay, so after the class, please go through this, what is SPF and how you can actually optimize this algorithm using the smallest prime factor. Okay. And then in the modular arithmetics, there is also Fermat theorem, which is very important. So just Google all these concepts and go through all of them. Try to solve problem based on all of them. Okay, they all are very, very important. They will help you in problem solving as well as in interviews. Okay, cool. So this is it for today's class. If you liked the video, if you understood everything, please like, please share it with your friends. Please tell us in comment which all topics you would want us to discuss next. Okay. Tomorrow's class is going to be on bit manipulation. So if possible, before joining the class, if you can go through how numbers are represented or what are the basic bit operations, then the class will go very smoothly, right? So next class is going to be on bit manipulation. So just read about some bitwise operators like OR, AND, XOR, left shift, right shift, etc. Just read about them. And if you found this video useful, you can just like it and share it with your friends. Okay.